All right, so now I'm going to talk about parallel plate capacitors, or parallel plate capacitance might be an even better word. You see the word here, capacitance, in all of these bullet points. Capacitance is a measure of how well a device stores charge. Okay. And so capacitance, it just so happens to be directly proportional to the amount of energy that a capacitor can store. And so if a capacitor has larger capacitance, then that capacitor can store more energy. Okay. And so I just wanted to outline that real quick. I also wanted to quickly outline where the symbol comes from. If you couldn't see it, this is the symbol for a capacitor, similarly to how this is the symbol for a resistor. It comes directly from this picture. So you can see that it's got the wire and then the first plate, some distance separating the plates, and then another wire. And that's exactly where this symbol comes from. Okay, and so this, as I said, capacitance is a measure of basically how well does a device store charge, and it's directly proportional to the energy. So more capacitance means more energy storage capability. And so capacitance is affected by three things. The first thing is this epsilon, which is the dielectric constant. And we can see that since that is directly proportional to the capacitance, we would expect that if this value goes up, then our capacitance goes up as well, right? And so that's exactly what I have here in the first bullet point, that capacitance increases with the permittivity of the dielectric. Okay, so permittivity basically is a measure of how well, so if this is my dielectric right here, this material, if I have an electric field that I apply across this dielectric, how well does this material polarize in order to store the energy in the form of that electric field? Okay, that's what permittivity is. So if I have more permittivity, then my dielectric constant will go up and my capacitance will go up. So different capacitors are made with different dielectrics. If you want a really high value of capacitor, then you need a very good dielectric, which has high permittivity. Okay, the second value here in the numerator is area, but it's not just the area of the plate. It happens to be the plate area overlap. Okay, so if I have two plates that, like say this is my first plate and then my second plate is over here somewhere, as I move this plate over, there's a little bit of overlap now. That would be some capacitance. As I increase the overlap, once it's maximally overlapping right here, that would be where I would get my maximum capacitance. And then as I were to move this plate away, this lower amount of overlap would result in lower capacitance. Okay, so the amount of overlap that we have directly determines the capacitance as well. And so if that area of overlap goes up, then my capacitance goes up as well. Okay, and so the third thing here that matters is the distance, this D, distance between the two plates. We can see that those are inversely proportional. So if I increase the distance between my two plates, then my capacitance will decrease. Okay, and so those are the three things that determine capacitance. And then typically I'll just give you the capacitance. I'll just, you'll have a circuit and there'll be some kind of a source. There'll be some resistor with some R, let's say 10K, and then there'll be some capacitor, 1 microfarad or something. And I'll ask you to do something with this circuit. I'm not going to give you epsilon and A and D most of the time and ask you to determine the capacitance. It's just going to be given to you. But it is important, it's practical to understand what determines the capacitance of a capacitor. It's also important to note, let me go ahead and erase this, that capacitance is measured in farads, like I said, or maybe I didn't say that. Capacitance is measured in farads, or F. So ohms is measured for, or is the measure for resistance. Farads is the measure for capacitance. But we're not typically, you've probably noticed by now in this class, if I haven't mentioned it already, that most of the resistors I use are in the kilo ohm range. I'm usually 1 kilo ohm or 20 kilo ohms or something. It's because the ohm is a very small unit, okay? So typically to get a sizable resistor, we need to use thousands of ohms. Well, it's the opposite for capacitance. Farads are an enormous unit, and so typically for capacitors, we'll see microfarads of capacitors, or which is 10 to the minus 6, or we'll see nanofarads of capacitance, which is 10 to the minus 9. Okay, so it's not common to see a millifarad. A millifarad is a very large capacitor, and if you were to actually get into the farads, then that would be absolutely tremendous. So just note that typically when we see capacitors, they're going to be in the microfarad or the nanofarad range. Okay, so I'll go ahead and wrap this up, and in the next video, I'm going to talk about the IV relationship for capacitors.